7.4, margin of error and confidence intervals. So what's margin of error? Margin of error is just a range of values that a measurement is said to be within. So think about like every time you hear in the news how they do polls and surveys, every result that they have is within some kind of margin of error. Now, when you're talking about margin of error, we are interested in having as the biggest sample size possible, the biggest number of people doing our survey, or the greatest number of measurements taken. Because the greater the sample size, the smaller your margin of error is going to be. Okay? The smaller the margin of error, the greater the accuracy. So if there's less error in your measurement, then it's more accurate. And for statistics with a probability of p, then the margin of error is defined as the letter capital E, which is equal to the z-score of that measurement times the square root of the probability minus the probability minus 1, all divided by n, and n again being the number of total, the sample size. Confidence interval. So the range of possible values that a measured statistic at a particular confidence level. So we're going to talk about confidence intervals and confidence levels. And the confidence level, the probability that a particular statistic is within the range indicated by the margin of error. So if you want to have a 90% confidence level, then you'd have to have a certain z-score for that. And the z-score for that is 1.645. Confidence level for 95% is 1.960, and the confidence level for 99% has a z-score of 2.575. Okay, so it's going to become clear what margin of error and these confidence intervals and levels are when we do a few examples. So example number 1. In a study of fish species, a researcher summarized the findings as lake trout make up 20.4% of the fish population in Lake Levi. The estimate is considered correct with plus or minus 3%, 19 times out of 20. You may have heard of this expression often in the news when they talk about elections and survey results. So what does this statement mean? So suppose the researcher samples the fish in the lake 20 times. Okay, because it's 19 times out of 20. Then the researcher can be confident that the percent of the lake trout found in the samples will be within 3% of this result, 20.4%, 19 times out of the 20 samples. Okay, so that's what that means. So again, 20.4% plus or minus 3. So it could be 23.4, or it could be as low as 17.4% of the fish population is made up of lake trout. And this researcher can be confident that this will always be the case every 19 times out of 20 samples that he takes. Okay, example number 2. Maybe I should write it out for example number 1. So suppose the researcher samples the fish in the lake 20 times. The researcher is confident. I think I misspelled research over here. No. So is confident that the percent of lake trout found in the samples will be plus or minus 3.0% of the result of 20.4% in 19 out of 20 samples. And that's what it is. Okay. Example 2. Lake Levi is one of the largest lakes in Algonquin Park. In 2009, 234 lake trout were caught out of a total of 911. In 2012, 141 lake trout were caught out of 689. Part A. Determine the percent of lake trout caught for each year. So for 2009, percent is 234 out of 911, which is approximately equal to 0.257 or 25.7%. For 2012, we have the percent is 141 out of 689, which is approximately equal to 0.205 or 20.5%. I'll write it over here, or 25.7%. Okay, so there are the percentage values. Part B. Determine the margin of error for each year using a 95% confidence interval. So let's start with 2009. So we have a formula. The margin of error is equal to z-score, times p minus 1 minus p over n. So the z-score for a 95% confidence interval is 1.96 times the square root. The probability of catching a lake trout is 0.257 and back in the year 2009. 1 minus p, so 1 minus 0.257 goes in the bracket. And I divide that by the total number of fish they sampled, 911. So if I carry out the square root and everything inside and I multiply it by 1.96, I will get a margin of error of 0.028. Okay, which says my margin of error is 2.8%. That's for the year 2009. For 2012, may be different. So let's calculate the margin of error. So E is equal to the z-score, again, times the square root of p times 1 minus p over n. So the z-score, again, is going to be 1.96. All that really changes is the probability, so the p-value and the n-value. So 0.205 times 1 minus 0.205, all divided by 689 fish that they caught that year. So when I calculate all of this, the resulting margin of error is 0.03, or 3% for 2012. Part C, determine the confidence interval for each year. So for an interval, we're looking at a lower limit and an upper limit. So for 2009, the lower limit would be the mean value, and we calculated the mean value, or the probability, I should say, the probability of lake trout being caught is 25.7%. So if the probability is 25.7%, with a margin of error of 2.8%, then I'm going to subtract 2.8% to get my lower limit, and that's going to be 22.9. The upper limit will be 25.7 plus the 2.8% margin of error, which would result in 28.5 as my upper limit. Okay, so the confidence interval is between 22.9 and 28.5%. For 2012, similar idea. You take, so for the lower limit, the percent of getting a trout in 2012 is 20.5%. So I start with that, 20.5. I add, for the lower limit, I have to subtract 3% because that's my margin of error, giving me a value of 17.1. My upper limit is 20.5 plus 3%, giving me an upper limit of 23.1. So, is it reasonable to conclude that the percent of lake trout in Lake Levi decreased from 2009 to 2012? So it looks like the lower limit has decreased from 22.9 to 17, and the upper limit has also decreased from 28.5 to 23. Does that mean that the percent of lake trout has decreased overall from between those 3 years? Well, I can say that, first of all, a 95% confidence level is used. So it's a certain amount of confidence here. But the two confidence levels intervals overlap. There is an overlap, okay? Because if the upper limit of the 2012 data is above the lower limit of the 2009 data. So that overlap means that the 2012 data could fall within the 2009 confidence interval. So you can't really definitively conclude that the percent of lake trout has decreased, right? Because what if that margin of error said, well, in 2009, my percent of getting lake trout was actually 22.9. I reached my lower limit. Then in 2012, you found that you were in your upper limit. Then your percentage of lake trout would increase between those 3 years rather than decrease. So because of that overlap, we can't definitively say for certain that the percentage of lake trout has decreased over the 3 years. Okay, example number 3. A pharmaceutical manufacturer makes more than 500,000 pills of a certain drug each day. The company randomly samples 400 pills daily to check that they meet the proper weight and size standards. On a given day, 52 pills were found to be substandard, meaning kind of like defective or not up to a certain standard. Part A, what is the margin of error for this sample at a confidence level of 90%? So for 90%, the z-score for this confidence level is 1.645. And the percent of pills found to be substandard would be 52 out of a total sample size of 400. So that is a 0.13 or 13%. So I'm going to make a note here that n is 400. So what's the margin of error? So the margin of error can be calculated using this formula that we used previously. So 1.645 is my z-score times the square root. The percent or the probability here would be 0.13 multiplied by 1 minus p, so 1 minus 0.13, divided by a sample size of 400. And that was going to be 0.028 or 2.8%. If the company would like to cut the margin of error in half, how would the sample size have to change? So this goes into that idea from the beginning. If you want to reduce your margin of error, you have to increase your sample size. How do I know this for sure? Well, just look at the formula. What happens? What happens if I increase my n, right? If I increase my n, then the entire, because n is a denominator, the entire quantity inside the square root becomes much, much smaller. And so if this becomes much, much smaller, then the entire right side becomes smaller, and thus the margin of error will become smaller. So if we want to half the margin of error, so half of 0.028 is equal to 0.014. Okay, so the error we want is 0.014. And so we set it equal to the rest of the formula. So the z-score 1.645, square root of 0.13, and 1 minus 0.13 is 0.7, so that goes here. And we're going to divide that by n. Okay, so now I just have to solve for n. And it turns out if you solve for n, working backwards, you'd get an n value of 1561. So you have to substantially triple, more than triple your sample size to test 1,561 pills, so that you can get as much half the margin of error, 1.4%. Okay, so repeated sampling. Suppose the samples of the same size are repeatedly taken from a population that follows a normal distribution, with a mean of mu and a standard deviation of sigma. Well, the means of the samples will be normally distributed with a mean of mu and a standard deviation of sigma x bar. Okay, so we're talking about the means of the samples being normally distributed with this population mean, but with a standard deviation mean for the samples. So the usual rule is that you should have a sample size of 30 to produce a reasonable estimate of the population. And you can calculate the margin of error for a sample mean using a simpler formula. over here, or another formula that we have over here. And this is known as standard error. Okay, so let's look at one more example. So a consumers group tested batches of light bulbs to see how long they lasted. The results in hours from one batch were the following. So all these different results for the hours of a light bulb lasting. Okay, the manufacturer claims that the life of the light bulbs is normally distributed with a mean of 1,200 hours and a standard deviation of 420 hours. So these represent our population mean and standard deviation. So calculate the mean of the sample and the standard deviation for the sample means. So what we're looking for is x bar, the mean of the sample. We represent by x bar, not by mu. So the mean of the sample is the sum of all the individual sample measurements divided by the sample size. So if you add up all of these numbers given for the batch that we tested here, all of these numbers would add up to 14,793. And if I divide that by the number of light bulbs we tested, so in one batch, we tested, looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we had 12 light bulbs in our batch. So the sample mean is 1232.75. So notice that it's not the same as the population mean. The sample standard deviation, sigma x bar is equal to the population standard deviation divided by the square root of the sample size. So the population standard deviation is 420. I divide that by the sample size, square root of 12, and I get a standard deviation of 121.24. So that is the standard deviation from a batch sample. Part B, determine the 99% confidence interval for the sample mean. So the 99% confidence interval, you see that confidence interval terminology, you have to think of z-scores. I need to know the z-score for that. So that's going to be 2.575. So the lower limit of my confidence interval is going to be the sample mean minus the margin of error. Okay, and since we don't have the margin of error, I'm going to use the formula provided up here to calculate my margin of error. So I'm going to replace E with Z times sigma x bar, because I already have sigma x bar. So I simply just substitute the values here. So I know my population mean is 1232.75, subtracted by the z-score, 2.575 for a 99% confidence interval, and multiplied by sigma bar, 121.24, giving me a lower limit of 920 hours. Similarly, you can do the same thing for the upper limit. X bar plus E, and that would give you an result of 1545 hours. So the sample itself will have a confidence interval between 920 hours and 1,545 hours. And that ends this lesson.